Thanks, Nathaniel.
Thank you for remembering that. Yeah.
Go ahead, Mary Lou.
So this one, Dale Gary from NJIT, who used to be in New Jersey, so I would get to see him then, has for a long time been in California at the Owens Valley Radio Observatory, which sounds like a fantastic site. I've never been there, but I'd like to learn a lot more about it. So Dale, tell us about it.
Okay, well, first of all, let me see if I can successfully share my screen. I think this is the one I want to share and start this.
Looking
No,
good.
okay.
So make it as a slideshow.
I think I want to do this, right?
Perfect.
Okay, wrong slide.
Well, I'll get the right slide.
Let's see, where am I supposed to be? Up here. Oh, I see. That's interesting. Okay, that was my talk. I hope you enjoyed it. All right. Yeah, thanks for inviting me. I hope I'm coming through loud and clear. You can hear me okay?
Yep.
So,
Yeah, you're coming through great.
okay,
Loud
great.
and clear.
So, yeah, I'm going to tell you about the Owens Valley Radio Observatory, telling you a little bit about the instruments, but also the science that we do with them. And, you know, we at New Jersey Institute of Technology, we operate some solar telescopes there. And so that's my main area that I have been involved in. But there are a number of other instruments there that I'll tell you just very briefly about what they are and what they're for. I thought I'd start out with the first two antennas on the site, which are these two here. Basically, this is a time when the United States was kind of behind Britain and Australia in terms of radio astronomy, discoveries and things. After World War II, the surplus radar equipment became used for trying to understand radio emission from the galaxy, from extragalactic sources, et cetera, and also the sun. And the United States was kind of behind the curve. And at around this time, in the late 50s, the Green Bank Observatory was formed to be the sort of site of a national observatory. But at the same time, places like Caltech were interested in getting into the game as well. And so because Australia had such a leg up on the technology, Caltech invited John Bolton in 1955 to come to the United States and build a radio telescope specifically designed to measure accurate radio positions for the radio sources. They had been discovered and located at low resolution, but it was impossible to identify cosmic sources that went with them optically. And so they really needed to measure more accurately the radio positions. So John Bolton came and helped construct this pair of antennas. That's an interferometer. And using an interferometer, you can identify spatial locations to a resolution that's equivalent to the separation between the antennas. Now, these particular antennas were actually on rails so that you could move them to change the spacing from close together. This is a photo when they're pretty close together, but they could also be moved further apart. And so starting in 1960, the observatory began to produce hundreds of radio source positions. The dish on the left is still in use today. We use it in our expanded Owens Valley solar array, but we don't point it at the sun anymore. We use it for calibration of cosmic sources. So on the left here is a more modern photo of those two dishes. They're separated a bit more on the rails in this photo. And at this time, they were being used to observe the sun. So you can see the shadow is centered on the center of the dish, which tells you that the dishes are pointed at the sun. So we used these for about 20 years actually to observe the sun. And we added some small antennas like you see on the right to form the Owens Valley Solar Array. The small dishes, the sun is so bright that one doesn't need a large collecting area to make good measurements. So the small dishes were just fine for observing, and of course much cheaper than the big ones. So we just increased the number of antennas by adding the small ones. But in 2012, we began to expand the array. It was really an entirely new instrument. You know, we ripped out everything and started from scratch essentially. But we added these more of these small antennas. These are a little more modern, so they have a high precision pointing capability. And this is a photo of the array around the time of its completion in 2017. I don't know if you can see, there's a little dot here in the very distant background. That's the most distant of our antennas. So these are the ones in the center of the array, and then we have a few scattered around, covering about a square mile of area, but covering that with only 15 small antennas. But using that, we're able to image the sun, and we operate in a frequency range of 1 to 18 gigahertz. So that's a very broad range of frequencies. And the reason we do that is to improve our understanding of the spectrum of the sun. So this is an example of what looks like 6 pictures in radio, but in fact, the one in the upper left here is actually from a spacecraft, and it's not a radio image. It's an image of the extreme ultraviolet, and you can see that the features in the satellite image look very similar to what we're seeing in the radio images. So we don't need to go above the atmosphere to see the corona, basically. We're seeing the corona in the radio from the ground, and that's one of the strengths of using radio emission. You can also see that the brightness of the features here, the contrast is much greater in the radio, except at the higher frequencies. So at lower frequencies, this is 3 gigahertz, 4.5 gigahertz, 6.9, 10.2 gigahertz, 13.9 gigahertz. So as you're going this way, the frequency is increasing. And what we're seeing is the effect of sunspots. So the sunspots are strong regions of magnetic field, which are increasing the brightness or the opacity of the corona and making it extremely bright. So let me play this as a movie. This is 1 image per day for about 12 days. And you can see the sun is rotating. Again, the extreme ultraviolet image, all the features, match up very well. You'll also notice a lot of distortions in some of the radio images, especially around the brightest. That's because of the limited dynamic range of the of EOPSA, with only at this time we had 13 antennas, and that does limit the ability to make images of the weaker emission. So this is a log scale, and we're seeing some very, very bright active region emission that's causing some artifacts to appear. But with more careful processing, we can remove those. So these are quick look images here. So that's one example of what EOPSA can do. But EOPSA really shines, if I can use that term, for observations of solar flares. And instead of once per day, the flares are so bright and simple enough in spatial complexity that we can image at in 1 second. So we have a 1 second time resolution. So what I'm showing here are 2 images in what I call true color. So the red, green, and blue color planes are apportioned by frequency. So we've got about 30 frequencies that we are adding together, but we put the low frequencies in the red plane, the high frequencies in the blue plane, the intermediate frequency in the green plane. And so that allows you to see the frequency content as in a single image. So yellow would imply that you're seeing the green and the green and red, sort of lower frequencies. Red, of course, would be the lowest frequencies. So let me play this first one as a movie, and you'll see it starts out here fairly kind of yellow and red, and then it turns into a pair of sources in another location, and they get redder and redder over time. So that's showing you that this is in fact a very large magnetic loop, and the two ends are rooted in strong sunspot magnetic fields. And as time goes on, the frequency of emission goes to lower and lower frequencies. The one on the right, you're going to see very early on a kind of a pair of sources on each side, kind of flanking the main source. And then you'll see it turn blue. And that's implying that it's very high frequency. And then later it turns yellow and red as it goes to lower frequencies. And you can also see, let me just play that one more time. You can see that it rises with time and forms a kind of a dome shape. So this is a magnetic loop again with the emission in it. So those are the kinds of observations we can make with Owens Valley. But what we're interested in is the spectrum. Okay, so let's go to another instrument that we have on the site. This is called the Owens Valley Radio Observatory Long Wavelength Array. And we're not using dishes now. We're just using these, what are called a bent dipole. And there's two different polarizations. So you end up with four different legs to this triangular kind of trapezoidal shaped antenna. And there are several of them here you can see. And the reason the night sky is shown here is because these are an all sky imager. You're basically imaging the entire sky. So let me show you that map, show you where we're located in California. So there's a Google image of the site, and this is the 256 element core. And later on, these additional elements were added, the blue lines, and then the orange lines are the current expansion. 352 elements. Sorry, did someone have a question? Okay, if not. Now, one thing that is exciting about this new expansion is that we've added solar dedicated modes. So we can actually study the sun with this instrument in detail with a solar dedicated capability. So we have a solar dedicated beam. That means that we're forming a narrow pencil beam on the sky, and we're pointing it directly at the sun at all times. And that allows us to obtain 3,072 frequencies in the range 15 to 88 megahertz. Okay, so this is a much lower frequency than EOPSA, but that allows us to see the higher corona and the larger features of the sun. We also have 1 millisecond time resolution. Now, we're not actually using such a high time resolution for the most part, but we do have the capability to do that. And we have a large beam that captures all the emission out to plus or minus 6 solar radii. But in addition, we have solar dedicated imaging using the interferometer to form images. And there we have 768 frequencies, again in that range, 15 to 88 megahertz, 0.1 second time resolution, and 1,128 baselines. And that gives us, at the highest frequency, gives us a 5 arc minute resolution. So as I said, this is an all sky imager. So before I go to the solar data, I wanted to show you what the sky looks like for the entire sky. These are 10-second snapshots. And what you're seeing again are a panel of multiple frequencies for one specific time. So there's 32 megahertz here, 36, 41, 46, 50, and it just keeps going up. to 82 megahertz in this lower right corner. Now, you can see some features there. This is actually the Milky Way. So you're seeing the entire sky, horizon to horizon. This is the east, north, west, south. And you can see a few point sources, which are the brighter point sources. So let me play that as a movie. You can watch the sky rotate. This is I think these images are about once per minute. And this is the sun, this kind of isolated source here. And basically we're making images of the whole sky for the duration of the time that the sun crosses the sky. Now, let me play this one more time because I want you to notice this particular frequency, 59 megahertz. You can see some things zipping around if you look carefully. Those are typically airplanes, sometimes satellites, that are reflecting channel 3 radio interference. So you'll get just a specular reflection off from an airplane, and it gets into the beam. So that's the whole sky. But as I say, the sun is also in the sky. So when these are quick look images, so when you properly process them, you can make images like this. So there's the Milky Way. There's a galactic spur out here. This is the region of Cygnus. You can zoom in and you can see a lot of features. These, what look like point sources, become actually supernova remnants, things like that. And this is the Cygnus loop. And all of these sources here, hundreds of thousands of sources in the sky, can be imaged on a very high time scale. So one of the things that this instrument does is it looks at the transient sky. It's looking for things that change, maybe appear that weren't there, or get brighter in unexpected ways. So it's really looking at the high time resolution sky all the time in radio. But as I say, the sun is in the sky. And so what we can do is make a cutout of each of these frequencies. These are 12 frequencies from 34 megahertz increasing to 84 megahertz. And this is a special day, actually. This is the eclipse from April 2024. You can see that the images kind of wander around. That's the ionosphere doing some refraction. It's moving the position. And now the moon is coming in. This is the moon is eclipsing the sun. And you can see it start to cover more and more. The optical disk of the sun is the white circle. So if there's no refraction, we would expect the source to land in that circle. But due to the ionospheric refraction, there is a shift. The day was very, very quiet on this particular day during the eclipse. And so there's not a lot of activity on the sun. It's just sitting there quietly emitting. You can see at low frequencies, the ionosphere is affecting things. You can see some kind of wave patterns. Some of this might be imaging artifacts as well, because we're imaging the whole sky and picking out the sun from it. The shift of the source position can be corrected, and that's because the effect is well known to have a 1 over frequency squared dependence. So because we have so many frequencies, we can identify that 1 over frequency squared shift and subtract it. This is 12 frequencies, but in fact, we actually observe at any time 144 frequencies. I mean, we actually can observe 768 frequencies, but it's really too many images and things don't change that much from frequency to frequency. So we typically are doing 144 frequencies. So this is just one snapshot of time during the eclipse, around the time of mid-eclipse, showing that 144 frequencies. And from those 144 frequencies, each pixel in the map can be picked out and form a spectrum. So this is the radio spectrum. And these are in brightness temperature units. So at the top here is 1,000,000 degrees. This is 100,000 degrees, and this is 50,000 degrees. So the sun is showing at about 700,000 Kelvin, and then it gets weaker and weaker as you go to lower frequencies. And then at lowest frequencies, of course, we kind of have the ionosphere affecting things, and we lose it for the quiet sun. Now, during bursts, we can do much better than this, but it points out that we can get these quiet sun spectra at very high time resolution. The sun was really quiet on this particular day, as I mentioned, but we did see one tiny source near the eclipsing moon. So this is just a snapshot at a time when we had this little source here, which shows up in the spectrogram like this. So this is frequency from 65 megahertz to 85 megahertz, and there's a little blip here that's some sort of probably electrons coming out from the sun in a beam, and they form this little source here right at the edge of the moon. As far as other instruments at Owens Valley, none of these are used for observing the sun. They're basically for cosmic sources. We have the Deep Synoptic Array, the DSA-110. This is an image showing just a few of those, 110 of these antennas spread around the array. They are located close together and with equal spacing here, but there are others that are in other spacings spread out over the site. And what these are mainly used for is to observe something called a fast radio burst, or an FRB. These aren't really good for finding FRBs, but they're good for follow-up. So when there's an FRB, or a fast radio burst, identified by another instrument with some rough localization, then these antennas can point to that location and make images of the afterglow, essentially, of the fast radio burst. These bursts are rather mysterious. We're not really sure still what causes them. They seem to be associated, at least some of them, with magnetars, which are highly magnetized, very large individual stars. But it's not clear at all how these bursts can be so rapid and so bright. They are very bright to be able to see them in lower resolution instruments.
Dale,
These instruments,
how long does the follow-up last? Does it go for a whole day or a whole week or 2 minutes?
well, let me mention that these dishes only move in declination, so they're a transit instrument, and so you have to wait for the sky to rotate to bring the source into your field of view, right? And
Okay.
then they can only observe for, I don't know, 10, 15 minutes on a particular source, and then it's rotated away. But and so they can follow up on a time scale of, very rapidly if the sky happens to be positioned correctly, or it might be almost 24 hours before it comes around. But these afterglows can take, last for weeks. So
Ooh.
what they want to do is identify with high resolution the location of those, and then have optical follow-ups as well. So there's also on the site a 40-meter dish. This is just a single dish, but it's a very, very large diameter. And so it gives you very sensitive collecting area for things like very long baseline interferometry, where you combine the signals with other large dishes around the world and do a kind of a radio interferometer of the size of the Earth. It's also used to monitor the radio flux from Blazars, which are active galactic nuclei. So this dish has been observing a set of Blazars sources for, I don't know how long, maybe 20 years or more, and observing as often as possible so that they can get the time history of the light curves from those active galactic nuclei, and in comparison with the Fermi gamma ray instrument in space. So they're able to combine their data and learn about little bit more about those sources. One interesting thing is this antenna was the prototype for an alternative to the VLA. So this was built in the late 60s. It's the only one that was built, but it had been planned to build 8 of them. And so you would have 8 40-meter antennas, which would be highly sensitive. But in the end, they decided that the very large array would be put in New Mexico and would have 27 antennas of a smaller diameter, 25 meters. So this is kind of an anachronism that it was built and then canceled. The project was canceled, but it's done a lot of work as a single dish. And then there's an array of antennas shown here that ultimately became the CARMA, the combined array for millimeter astronomy, combining with some instruments, some radio telescopes in Berkeley, and another experiment that was at the South Pole for a short time. But unfortunately, that instrument got defunded when ALMA came along, the ALMA millimeter array in Chile. So now the individual antennas are used for different things. And one of those antennas is used with a feed array to map carbon monoxide intensity in the universe. And so they use the intensity as a function of frequency, which gives you a function of redshift. So you'll be able to identify the carbon monoxide in external galaxies at different redshifts and map out, sort of a 3-dimensional picture of the carbon monoxide in the universe. So let me go back. I know most of you know all of these issues, but I want to kind of touch base with where radio waves come from and how they're produced, and a little bit of the physics before I go into the science. So obviously radio waves are produced anytime you have an accelerated charged particle. And if you were to have like a sinusoidal electrical driving of electrons up and down this antenna, it will produce a sinusoidal time domain signal radiating away. And in the time domain, this is a very pure sine wave, you would end up having a spectral domain of just a line. So it'd be a single frequency. Hot objects produce radio emission, and high energy particles accelerated in solar flares or jets from black holes also produce radio emission. It's quite different though. This is a photograph of Centaurus A in the optical, and superimposed are some radio lobes that are being accelerated from a black hole in the center of Centaurus A. So this is a jet where the high energy electrons are moving out, and then they collect in these lobes at some distance from the galaxy. And if you were to look at the time domain of that sort of emission, it's going to look just like noise. And if you were to listen to it, it would just have a hiss sound. However, if you look at the amplitude as a function of frequency, so this time domain noise contains many frequencies, but the intensity of those frequencies is not necessarily the same. In fact, in the spectral domain, you'll typically have some broad distribution of frequencies, but some band of frequencies will be much brighter than other bands. So you'll end up with a spectrum shape that looks something like that. So that would be a typical, let's say, a typical synchrotron spectrum. The point is that the shape of that spectrum tells us a lot about the environment in which those high energy particles are residing, as well as a lot about the particles themselves. Hot objects also would have a hiss sound, this kind of a noise-like time domain, and might have a similar spectrum. But but they will typically radiate as a black body, more or less. And a black body has a very specific curve shape. So this is a black body spectrum for something that is 1,000,000 degrees, this dashed line. And the corona, the solar corona, is at 1,000,000 degrees. So if the corona were optically thick, that is, if it were operating, emitting like a black body, it would have an intensity that followed this curve. That would be very bad for us, since up here is the sort of gamma ray or hard X-ray part of the electromagnetic spectrum. And if it were this bright in X-rays, it would just fry us completely. So luckily for us, the corona is not optically thick at these frequencies. Now, what do I mean by optically thick? What you can think of as a photon will be emitted, and then it has some chance to escape or some chance to be absorbed and re-emitted. And if the photon is continually being absorbed and re-emitted, then that will be optically thick. So the photons cannot pass through. They get bounced around and they eventually come out after some last scattering. But typically they will not be able to come directly out. However, in gamma rays or X-rays, the corona is extremely optically thin, which means that once the photon is produced, it comes right out. It's not going to do any scattering whatsoever. And so that makes it very much less bright. The corona becomes very much less bright. It's just very wispy and thin. However, if you go to lower and lower frequencies, eventually you come to a point where it is optically thick. And this is the radio spectrum. So this is 10 gigahertz here. This is 1 gigahertz here. So these are the range of frequencies that EOVSA is observing, 1 to 18 gigahertz. And it's precisely that range of frequencies where the corona can become optically thick. That just means that these low frequency radio waves will get reabsorbed in the corona and scatter and then escape eventually. And they will form this part of the black body spectrum. So this emission is optically thick at 1,000,000 degrees, but we can see it optically thick, which is why it makes it so bright. So what causes the radio emission? As I said earlier, radio emission is very generally caused by accelerated electrons. So any way you can accelerate a charged particle, particularly electrons, they will cause them to emit radio emission. So in the solar case, the electrons are spiraling in the coronal magnetic field. And the stronger the field, the higher the frequency of the spiral motion. So if you look at the spectrum for a region of different magnetic fields, you'll find that spectrum is shifting to higher and higher frequencies as the magnetic field gets higher and higher. So by measuring the radio spectrum, we can directly measure the coronal magnetic field. And the radio emission is the most direct way to do that. Also, the higher energy of the electrons, that is their velocity, the brighter the emission becomes. So by measuring the radio spectrum, we can also measure the electron energies. And in the case of solar flares, the energies are in the range of 300 keV to 1 MeV, mega electron volts. That's a very, very high energy. Mildly relativistic electrons. So the speeds are close to the speed of light, maybe 0.8 the speed of light. And the temperatures, corresponding temperatures to these energies, are 1 billion Kelvin. So that's how bright that optically thick emission from solar flares can be. In fact, the one burst that I showed you a few minutes ago was 10 billion Kelvin, 10 to the 10 Kelvin. So extremely bright. So let's back up and look at how the sun produces this emission. So a white light photograph of the sun, you can see these sunspots here, these darker regions. Those are places where the magnetic field is very strong and is sort of inhibiting the heat flow. And so they appear to be darker than the surrounding part of the sun. If I zoom in, you can see that there's some structure here. And around the sunspot is this area called the penumbra. Next to the darkest is what the penumbra means. And you get these sort of striations. And those striations kind of look like what you might see with iron filings around a magnet. And in fact, there's a precise analogy. The plasma around the magnetic field of the sunspot is conducting. It's just like the iron filings, and they tend to move along the magnetic field and not across it. So they outline the magnetic field shape. Now, magnetic fields have north and south poles. And so hopefully you can see this sort of thing. We can also observe the surface of the sun in magnetic fields. And so the sunspots are regions of strong magnetic field, but there's also strong magnetic field outside them. And in this display, the white is the north polarity and the black is the south polarity. So this is an image of the sun in magnetic field strength. You can see the regions of strong magnetic field strength, some of which are sunspots, and other regions that are enhanced magnetic field, but kind of spread all over. And you can see it's mainly white here, north polarity, mainly dark here. So those set up very large scale magnets, if you will, large scale loops joining the negative to positive. And if we extrapolate that field from the surface, we can get what's called a potential field extrapolation, which is showing us where the magnetic fields would go if there were no currents flowing in the corona. And this is an image of the extreme ultraviolet, where you can start to see some of those loops. And if you compare the field lines from here to here, you can see there are some similarities. You can see some large scale loops here, but there are also quite a few differences. And the reason those differences are there is because when you have a current flowing, you know that you can make an electromagnet by connecting a coil of wire up to a battery, and that produces a magnetic field. So that current produces a magnetic field, which is not represented in the surface fields that you're mapping. So when we do a potential field extrapolation, we're ignoring any currents that might be in the corona. But those currents are there, and they modify what the magnetic field is like in the corona. The current is the source of free energy that powers solar flares. So we're very interested in that current. We want to understand where it's strong, how it can be interrupted, and what it does to the particles in plasma when they occur. What we have developed over time is something called the standard solar flare model, where you have sunspots here. There's just a cartoon showing that there's a loop connecting the north and south poles of a magnet of the sunspots. And above that, these loops can start to expand and actually leave the sun. And when they do that, they can pull, they've essentially evacuate the region behind it. And so the magnetic fields can start to approach each other here in the middle. And this produces what's called an X-type neutral point. And that's where the solar flare can be generated, where these magnetic fields are coming together. They can actually pinch off. What's left is more potential. It has less current in it. And those currents get interrupted essentially and produce the energy to power the flare. So let me show an actual flare. This is a very large flare from 2017, September 10. Let me first show it to you in this extreme ultraviolet movie, and you'll see the flare occurring right about here. So see some activity, and then boom, there it goes. And hopefully you saw that kind of loop that lifted off. And And then over time, these slowly evolve to, these magnetic fields slowly evolve. Let me just play that one more time. So you can see this loop just goes off. You see a lot of other motions caused by a shock wave that propagates along or around the sun. So I'm going to replay this movie here. Actually, I'm going to play these together if I can. Oops. Okay. Sorry. This is a close-up of that movie. Let me play it again one more time and play the radio image at the same time, and you can see the radio emission is this really bright stuff here is actually dark in the radio, and that's because although it's bright in extreme ultraviolet, it's bright at a lower temperature, and some very high energy particles are just above that. So this is outlining the relativistic particles above that bright loop emission there. So these erupting magnetic fields drive powerful coronal mass ejections. So now I'm going to show you a movie. This circle is the sun, and this is an artificial eclipse. Essentially, you're putting an occulting disk in front of the sun to block off that extremely bright emission. And you're going to see the coronal mass ejection occur over here. And when I play the movie, you're going to see that thing move very rapidly outward. And then you're going to see a lot of kind of noise in the entire image. And that is due to particle radiation. The particles accelerated by that rapid ejection of coronal mass. Those particles eventually reach the spacecraft, which is near Earth, and produces that noise. So there you go. And you can see all this noise from those particles hitting the CCD detector near the Earth. So that particle radiation is dangerous to spacecraft, astronauts, and even on aircraft flying polar routes over the poles of the Earth. The radio emission allows us to study the initiation of those events. So that's what we get from the radio emission. So let me just give you one example of that, and then I'll move on. But if you take a snapshot of a multi-frequency image, so this is just one particular time, but at, what is this, 28 different frequencies. And you can see that the shape, again, we have low frequencies here, increasing to higher frequencies down here. And you can see the shape does change with frequency. That means the distribution of brightness is slightly different at different frequencies. And also, of course, the brightness itself can change. So if I take this, this is like one of these true color images at this early moment. And if I look at this particular pixel, number 1, that's this spectrum. So I'm taking that pixel in each of these images and just plotting its brightness as a function of frequency, and this is the brightness in some in solar flux units. So that particular location has a spectrum that looks like that. This line is a theoretical fit to those points. If I look at point 2, that looks like this. If I look at point 3, it looks like this. One of the things you can notice is that the peak of the spectrum is shifting to lower frequencies as we go upward. And that's exactly due to the fact that the magnetic field strength is going down as we go up. So as the field strength goes down, the peak of the spectrum also goes to lower frequencies. So one of the parameters of this fit is the magnetic field strength. So if I just show you what those are, we have 520 Gauss for this fit, 299 Gauss for this fit, 148 Gauss for this fit. But we don't have to do this at just 4 pixels like this. We can do it at every pixel of the map, right? And so this is an image of magnetic field strength. We've basically done this exercise for each of these pixels, and we're plotting the brightness or color, I should say, is proportional to the magnetic field. So this bar here is indicating 200 Gauss, 400 Gauss, 600 Gauss, 800 Gauss, 1000 Gauss. So the strong fields are yellow, weak fields are blue and green. So now I'm going to play this as a movie. You can do this at every time during the flare. And you'll see a lot of details, but you can notice that it's getting bluer and darker over time. And what that's telling us is the magnetic field is getting weaker and weaker in this location. And that decreasing magnetic field corresponds to a release of energy. That magnetic field is being converted to these high energy particles, the energy to produce these high energy particles. That's just an example of the kind of thing you can do with the radio spectrum measured by EOPSA. Okay, going on to OVRO LWA. Again, this is this all-sky imager. This is the beam spectrogram from one of the bursts that we observed with the array. And you can see that there are some strong bursts, kind of vertical features here, and then there's some more slanted, if I can call it that, features here. So this is the sort of 20 to 88 megahertz range. Down here, you have some problems with the ionosphere being opaque, so you can't really see through it very well. But at the higher frequencies, you can see the emission. Now, this is a typical sort of finder chart for the kind of the bursts that you will see in the from the sun. And this is time in minutes, and this is frequency going to lower frequencies. And the reason we plot it this way is because high frequencies mean low altitudes and low frequencies mean high altitudes. And so if I take this and flip it, that is going to show you this kind of behavior. So these vertical things here are called type 3 bursts. These are beams of electrons moving rapidly, relativistic electrons moving away from the source, going out through the corona. These more slanted ones are called a type 2 burst, and that's due to a shock wave that's associated with this bubble of magnetic field that's moving rapidly away. But they don't move as rapidly as these relativistic electrons, and so they slope more slowly with time. And then behind that, you'll sometimes see noise storms of various types. All right. OVRO LWA is measuring in this range of frequencies, and EOPSA is measuring way down here. So we're seeing the near surface stuff with EOPSA, and then with OVRO LWA, we're seeing the consequences of this material that's moving rapidly away. This is a cartoon again of that flare model. The main driver of the flare is the release of energy here. It accelerates particles that are trapped in these lower loops, but they also can move outward. And the type 3 burst has to have an open magnetic field line. It has to be able to escape the region of the loop. And so you'll have type 3 bursts along this open magnetic field line, green being higher frequency, red being lower frequencies. So they, as a function of time, this thing moves along and goes to lower and lower frequencies, but very rapidly. The type 2 bursts would be associated with the shock wave, some sort of a region just ahead of the CME, a coronal mass ejection that's being pushed out. And you might have type 2 bursts that are coming from the very tip of the CME. That would be like this. And you might have emission from the flank because the shock wave can go sideways as well. And those would be at higher frequencies, which would be lower heights, which would be this sort of thing. So you see the whole picture all at once. And then the type 4 burst would occur somewhere down here. And that's what we see with EOPSA, but we can also see it not so much for this event, but other events, you get a lot of type 4 emission. Okay. So let me, if I just have a couple of minutes, I wanted to say a few things about science of interest, perhaps to HamSCI. One thing is the traveling ionospheric disturbance. So this is again a spectrogram. This is a time when there's not much going on in the sun. So this emission is just the background quiet sun emission. These are type 3 bursts that are zipping through the, not associated with flares necessarily, but just little accelerations of particles that are zipping out from high frequencies to low frequencies. But what I'm interested in is this darkening here and maybe this brightening on the edges. And if you look at the images associated with that, so this is two different frequencies. And different times. So this is 1609 to 1632. And what you'll see is the image of the sun. Each of these dots represents one of these images. So this image would be this dot. So we're well away from the event. And you can see the sun looks pretty normal. And then it starts to get distorted. It actually gets stretched. And this particular white dot corresponds to this particular image. And then it goes through this darkening and actually separates into two and then becomes very narrow. So here it's stretched, here it's narrow, and then it goes back to more or less normal. And this is the same thing at a lower frequency. You can see again, you start out before the event, the sun looks pretty normal. It starts to get distorted, stretched out, and then it gets compressed, actually breaks into two, but becomes very narrow right in the middle here, and then becomes normal again. And if I plot the time profile of the brightness, you see that the brightness gets very bright here at the time when it's stretched, and when it gets very narrow, the brightness gets much weaker. These are three frequencies during this event. So what this is a traveling ionospheric disturbance. It's something that is like a density enhancement in the ionosphere that is traveling across the array and going in front of the sun and causing all these distortions. And here's a model of a simple model for a traveling ionospheric disturbance. Let's say you have a wave of density. So there's a high density, low density, high density, low density. And to help visualize that, I can kind of show the inverse of this, so that this would be like a lens, right? This would be a region of high density, like you might think this is a converging lens and then a diverging lens. But in fact, the rays going through a high density are going to diverge because they tend to refract away from the high density. And where the density is low, it's more like a converging lens. And if you look at what the sun should look like at these times, when it's diverging like this, it's going to look like it's narrow in one dimension. When it's converging like this, it's going to look broader. And so you can see a traveling ionospheric disturbance would alternately make it narrow, broad, if it were kind of uniform. Now, in this particular case, here, this was a single event, just one wave that went by, but other times you'll have a train of such waves. Now, if you look a little more carefully, you find a model for the ionosphere is that these waves, they tend to slant in the direction related to the magnetic field. So this magnetic field line here, this is the dip angle of the magnetic field, and these waves are going to, these disturbances are going to align in the direction of the magnetic field, but not following exactly along the magnetic field. So the ridges and troughs of the gravity wave are tilted in the direction of the magnetic field, but they don't align with it. And when one ray traces through the model, you find the greatest focusing or dispersion effects will be when the sun is aligned with that, right? So if the sun happens to, the look direction to the sun happens to be aligned with one of these channels, then you're going to get a lot of refraction. And so this is an example of from a paper in 2018 where they were examining this, and the green stuff here is supposed to relate to the density of waves. So the waves are going to focus in these channels and be bright here. But if you look at this as a function of frequency, you'll find that they focus at one frequency at the ground, but at another frequency, they'll focus higher than the ground. And so they'll end up being diverging lower. So if you look at this as a function of frequency, you'll have various effects caused by the focusing being a function of frequency. And they were trying to explain this kind of spectrograph record where, and I would call these things caustics. And so again, you have a high level of focusing at maybe 60 megahertz here, but then they defocus at lower frequencies. And this is a disturbance with multiple peaks as it moves along. So it's really interesting how these this imaging of the sun, we don't like these distortions, but the distortions themselves can tell us a lot about the ionosphere and these traveling disturbances. Another thing that might be of interest is shortwave fade-outs. So this is an example of that. There's a big type 2 burst here. There was a weak noise storm going on. Then the type 2 burst occurred, which is, again, the shock wave associated with the CME, and then a noise storm from enhanced noise storm from behind the coronal mass ejection. And if you zoom in here, you'll notice this stuff is radio frequency interference, and you'll see it fades out here right about 1700. It kind of goes away. So that's due to solar X-rays from the solar flare hitting the ionosphere, causing the ionosphere E region to start to become disturbed, and causes the shortwave not to propagate as far. So let me just conclude by saying the Owens Valley Radio Observatory has quite a few operating research instruments now, monitoring and providing research data for a wide range of astrophysical phenomena. Some of these are state-of-the-art, such as EOPSA, OVRO LWA, and DSA 110. And each of these are just pathfinders, in fact, for much larger facilities planned for the future. And DSA 110 is currently being superseded by an instrument that's already funded and is beginning to be constructed in Nevada, so in the nearby state of Nevada. And this is DSA 2000, nearly 2,000 antennas in a much larger footprint that will give better spatial resolution and sensitivity. And by the way, these dishes are fully steerable, so they don't have to rely on the transit and waiting for the sky to go by. And that's funded by HamSCIence. The DSA 2000 plan also includes a larger version of OVRO LWA, so they will be producing, similar antennas for OVRO LWA, but in much larger numbers and over a larger footprint on the ground. And EOPS itself is also a pathfinder for something called PHASER, the Frequency Agile Solar Radio Telescope project, and that's now in the proposal preparation stage. If this goes forward, which we certainly hope it will, it would also be at the same site as the DSA 2000. So all three of these instruments would be located there. So I'm afraid I might have gone a little long, but I'm finished now. I'll take questions.
Very cool. Okay. Questions? How many acres do these antenna farms occupy?
Yeah, the DSA 2000, which is the new one going in Nevada, is I don't know how many acres it would be, but it's about a 21 kilometers by 15 kilometers, something like that. So it's a very, very large, it's basically taking up an entire valley in Nevada. The ones that we currently have, I think the longest baselines are around 2.5 kilometers. So again, I don't know the conversion to acres, but you're talking about square miles of real estate being covered.
If one goes there, could one have a tour of the facilities, Dale?
Absolutely, sure. Yeah,
Cool.
just let me, or I actually didn't mention, I'm the former director, but I've since retired. I should have mentioned Bin Chen, who's at NJIT. He's the new director, and he would be happy to help you arrange a tour as well.
Do they have a visitor center and anything for public tours?
Not a visitor center per se. They have some posters on the walls, and they do have a yearly, once yearly public tour open house. But I wouldn't wait for that. If you want to get a tour, just drop us a line and we can arrange it. So
Cool.
there's one guy on site who is sort of the person that gives the tours. So he's very knowledgeable and can give you a good personalized tour of things.
What's the name of this tour person?
Mark Hodges.
We need to find Mark Hodges. Okay.
Yeah. So let me just quickly do a new slide. So MWH at Caltech.edu. Mark Hodges. If multiple people want to arrange something, it's best to try to do it together rather than having 100 people come one at a time. But
So we'll see what Nathaniel can arrange.
there you go.
I had a question, Dale. What's the scale size of those traveling ionospheric disturbances you had?
That's a good question. I think so. Their duration, when you do see them multiple times, they have a typical separation of about 20 minutes or so, 20, 30 minutes. And I don't know their speed. Actually, this model was meant to match these observations. So I guess we can just see what that shows. Oh, now I've got the wrong. Let me go back here. So looks like the separation here is around 300 kilometers.
Okay, so those sound like medium scale traveling ionospheric disturbances.
And certainly
Is
not
there
large scale, yeah.
No, definitely. Yeah. So I think medium scale. Is there anything that you want to know about them that you don't know?
Well, I think one thing that is like this is a model for the shape of them, but I think that having the distortions of the solar data would allow you to add more knowledge about the specific shape of them. I have to say I'm not an ionospheric scientist, so I don't know what questions may be new and interesting, but I have a sense that this is aside from this kind of explaining the spectrum with no spatial resolution, adding the spatial resolution, I would think could be of interest to understanding how the disturbances form and how they, the spatial structure of the disturbances.
Thank you.
What date is this one? Do you have a date on it?
The one that here was May 1st, 2024. But these happen quite often, these kinds of, associated with this is something called ionospheric scintillation, which these large scale scintillations, which happen all the time in the data and are well known for astronomical objects. But and again, by the way, the alignment of the sun with one of these channels really makes the effect much larger, right? If you were looking through multiple of these in some other direction, you would not see such a strong effect. So they tend to occur in our winter time because that's when we're, because these are tilted to the south. So when we're looking at the sun at low elevations of the south, that's when we'll see this most of the time.
How about if the sun is low in the summertime, so just coming up or going down? Would you see the same thing? It wouldn't be in the, but east or west.
Again, I think the orientation of the disturbances would matter. I have a feeling that these things typically are traveling north to south or west to east. So, but the dip angle of the magnetic field is to the south, right?
Yeah.
So if they align again, they don't align with the magnetic field, but they tilt in the direction of the magnetic field. So they would typically be more prominent, near the meridian, I guess. But and one of the things I would like to do is you can kind of map these disturbances with the with GPS, right? And we have just with Lindsay, a professor at NJIT, Lindsay. Why am I blanking on her
Lindsay
name?
Goodwin?
Lindsay Goodwin. Yeah, she provided a dual frequency GPS receiver, which we've added to the site. So it's attached to our building there. And we haven't really compared the data from that with the observations yet because it's fairly new, but that's one of the things we'd like to do is compare the GPS disturbances in different directions, the delta TEC, with what we see.
Gwen had a question. What was your question, Gwen?
Hello. Thank you, Dale. Fascinating presentation. I was wondering whether the calibrated amplitudes of the solar radio bursts you observe might be at all useful to estimate the antenna factors of ham-size receivers above 20 megahertz. As I might imagine that this would be sort of a uniform amplitude source impacting on a scale of, let's say, the continental USA all at once.
Mm-hmm. Yeah, one thing that we can provide is very well calibrated flux densities from the sun, and I think that's something new because we have the imaging and we have the very well characterized antenna beam patterns for the individual elements and all of that. That we would be able to provide, within a few percent, I think, of the total flux that's actually there. So if that's helpful for characterizing your antennas, I imagine that would be.
I think that would be worth pursuing,
Yeah.
to say few percent, for the practical radio amateur. We might think in a few decibels rather than percent.
Yeah.
So clearly you have precision measurements. It'd be
Exactly.
worth exploring, Dale. Thank you.
Yeah. Yeah, just let me know. I can give you more information about how to access the data if you want for a particular day or that sort of
Excellent.
thing.
Yes, that's right. It's just some events will give us a handle on it. Thank you.
Yeah.
Yes.
Yeah. Great.
Any other questions?
I had put one in the chat. I was curious about your coverage of extreme solar events that have happened in the past, because I was thinking about all the decades of history you have for the facility, and like 2003 Halloween, 1989, those kind of big events.
Right. Yeah. So we did make observations of those, some of the Halloween events. They are, some of them occurred at nighttime for us, but the ones that didn't. So we do have data for those. One of the, I didn't really mention this, but one of the sort of famous ones that we observed was in December 2006, where there were a series of large flares, and we observed one which was actually the record breaker for radio emission coming from the sun. And the radio emission was so strong in the polarization that GPS uses that the GPS signals being received, by receivers was confused by this very bright solar source in the sky. Even though they're not directed at the sun, they were getting enough radiation from the sun to cause them to lose lock on GPS. And this occurred over the whole sunlit hemisphere, right? All at once. For about 10 minutes it went on. So that's been written up in a number of places. But yeah, that was quite an exciting thing. And what was interesting is that burst was highly polarized. So we measured it in right and left circular polarization, but only the right circular polarization happened to be really strong. These emissions are often highly polarized. So, but the right circular polarization is the same polarization GPS uses. So that was maximally bad for GPS.
Thank you.
So I have a question to follow up Sarah's question. I thought that was great. Do you have on your website a section where it says, look for the famous ones, and you have the 10 famous ones listed or something?
Yeah, not really. We're mainly
You see to
kind of,
that.
yeah. Yeah, we're sort of focused on what's happening now. So we have a number of things that if there's an event occurring now, you can get on the website and see that. By the way, I'll put it in the chat here. The HTTPS.
Use your microwave.
Sure.
Data.php. Yeah, so if you go there, you can see the current status of the array and with a number of different types of displays that are showing current data. And from there, if you click on some of those, they'll take you to movies and things. We also, if you just leave off the status.php and just go to the main page, you'll see other links to our data of various types. And
I have a question here.
Yeah.
First of all, thank you for an extremely interesting presentation here. Well, two questions really. Number one, we in HamSCI got a whole bunch of data from the last solar eclipse. Is there any effort going on to possibly coordinate the two organizations' data to try and integrate, or say that, okay, the hams saw one thing and this is what your data coming off the sun showed, so maybe there's possible to do some coordinated research on that effort.
right. Now, I saw a plot by that Gareth showed about I guess it was delays of WWV signal through the eclipse path, and it's a really interesting signal there. We haven't. I was involved with some telecons to kind of put this data together, but I think that's kind of died away now. I don't know. You get some excitement around the eclipse time, and then people kind of leave it aside. But it's a good point. I don't know enough about the kind of data that you're taking to know how we might help, but we'd certainly be glad to.
Yeah, I'm thinking that it would be just a good project, possibly for a graduate student or
Right.
somebody who was really into trying to take two different databases, combine them, and or try and coordinate them together and see what can come up. The two databases. The other question is are you available to make a presentation to my local amateur radio club?
I suppose I could be, especially if it can be similar to the one I just gave. So I don't
Oh
have
yeah,
too
and it would have to be shorter, of course, but we can talk about that. Could you please put your contact information in the chat?
All right.
Thank you.
Yeah. By the way, this is a different email than I think Mary Lou was using, but this is the one that's probably best for me.
Thank you.
Yep.
Anybody else?
I appreciate everyone staying longer to.
I think it
That was fascinating.
wonderful.
I mean, we in HamSCI do a campaign and we talk about, gigabytes of data, and we think that's a lot. I can only imagine how much data that's been processed off of that array over, not just recently, over your career and stuff. It's mind-boggling.
Well, especially the OVRO LWA, the data volume is tens of terabytes a day, and we basically keep the data for 7 days and then make our images. And if anything that doesn't get made is lost because we have to delete the data to go on to the. So we have a petabyte storage system, but we still can only keep 7 days at a time.
Wow. Wow.
Wow. Okay. So thank you very much. I'd just like to announce that a month from now, what is the date? The 13th of November is our next meeting on this channel. And Rob Suggs is going to talk. He's from NASA at Huntsville, Alabama. He's going to talk about meteor scatter and how ham radio signals can bounce off the ionized trails that meteors leave at sort of ionospheric altitudes, and what we can learn both about the ionosphere and about the meteors themselves from our observations. So see you next time. Bye.
Hey, Mary.
Thank you very much, Mary Lou, for
Thanks,
arranging.
everyone.
Yeah, weren't we also gonna have an informal get together?
Yeah, we probably will next week, Ron.